So there are two forms we asked you guys about. Those two forms, and no one had any idea. Or maybe you knew them, you just didn't know what they're called. Standard form, x squared gx to c for a quadratic, and then this one called vertex form, also known as parabolic. Darn quadratic stuff. There's a lot of information in a quadratic equation. You can get an idea of what the graph looks like. You can get a feel for where the vertex is. You can get an idea for intercepts. And then there's the application component to this. We're going to just dabble in the graphing part of it right now. And then what information we can get from the equations. So the two different equations are useful in a couple different ways. So we highlight right here what you would find in each of them. Quickly you can find the y-intercept in the standard form because that's what c is. So without doing any searching, really, I have the y-intercept, which is the c value of the standard form. And there's only one y-intercept. Every parabola will have a y-intercept. It will cross the y-axis eventually. Now the rest of the stuff, we have a little work to do. Now line of symmetry, axis of symmetry, they are the same thing, so you might see or hear them referred to as being either of those things. But it's the vertical line, we're talking about y equal x squared parabolas. It's the vertical line that splits the parabola in two equal pieces. It's that line of symmetry. Cuts it in half. Does this look familiar? I hope that looks familiar in more than one way. That looks familiar because we've probably seen it before. It's also part of a formula we use. What's that a part of, Braulio? Take a look at I got a sketch. Braulio, hello, or Braulio. What's going on right here? Negative b over 2a. What formula is that a part of? It starts with a q. Well, shall we remind ourselves? What is it? Quadratic formula. It's a part of the quadratic formula. Negative b over 2a plus or minus square root of b, right? So it's a part of the quadratic formula, and again, it's telling me where am I centered on my X-intercepts. So I use that in standard form. I use this to help me find the x part of the vertex. That's an important component there. That helps me find the. Now, if I had an application problem, this would be something that like says, where is the maximum occurring? Or if you're talking about height and time, that's going to be how long does it take for the object to get to its highest or lowest point type of a thing. But that's the x part of the vertex. Remember that a vertex is a coordinate. And then to find the x part, you plug that in. And that's the part that we seem to forget. Is if I want to find the y component of the vertex, same thing as the function notation f of x, which is the same thing in this notation over here of f of negative b over 2a. Yeah. Plug that value of x in, find the y. Now I got the vertex. So a little work finding the vertex is standard. A little, not a whole. From the standard form, what else can we find? Well, this a here can tell us a bunch. It can tell us if we're opening up or down. It can tell us if we have a max or a minimum value. Positive opens up, has a minimum. Negative opens down, has a maximum. All right, now that's about all there is review-wise on the standard form. One we're probably most familiar with is that. But there's this other cool form that is derived from the standard form. We're going to be able to do that. We're going to be able to take standard form and put it into this other one. It's easier, actually, to go this way. It's easier to go from parabolic to standard than it is to go from standard to parabolic. That's the easier route right there. Because all we do in standard form, parabolic form, is we can FOIL x minus h squared out, multiply a through everything, add my like terms, and then I have ax squared plus bx plus c. Yeah? All right. Hey, how'd you do, Summer? How's the swim meet? Was the pool cold?
No.
No.
It was
Did you win?
Me?
Yes.
I
Of course.
guess
Swimming is like an individual sport mostly. I guess there's a team aspect of it. You guys won. Was it an invitation?
I think we might have won. I don't know. It was an invite though, so there was.
So invite only varsity athletes.
No, JV.
Oh, JV was invited also. Where was it?
It was at Jesuit.
Okay. All right. Very good. Parabolic, vertex form. AHK. So now in here, so in the last one we can find without any work y-intercept. In this one, this has a little bit more to offer. In this one we can find the vertex without any work. So instead of doing negative b over 2a, plugging that value of x in, finding y, and then coming up with a vertex. In this form, HK is your vertex. That's nice. That is my vertex. Now notice, though, that it's not negative h positive k. It's the opposite of what you see. So if that was an x minus a 4 squared plus a 7, if it was that, then my h would be a 4 and my k would be a 7. All right. And then for either of those two forms, standard form, vertex form, anytime I want to find x-intercepts, make y equal 0, factor or quadratic formula, or complete the square. And then y-intercepts, well, we don't have to do any work with standard form, but in the parabolic form, we'd have to make x equal 0, and then find y. So there we go. There's our review of our two forms, and we're just going to practice graphing them and then writing one into the other. Again, a little info about what happens with that A. The A is the stretch factor. Vertically stretches my graphs, or shrinks my graph. If my A is bigger than 1, I stretch. Less than 1, I shrink. So my graph gets narrow if I stretch, and it gets wide if I shrink. Yes, ma'am. Any question? Yes!
It sounds like A is less than 1,
Yeah.
and they have to be negative, and then it sounds like A is negative,
Oh, that's a great question. Thank you very much. Because these should say the, I don't know, absolute value. You're right. If it was less than 1, I could be 0.99, which isn't negative, right? But it could be negative 4. So what we thought, we think about when A's, we're talking about the absolute value of them. So the negative part would just tell me I flipped it over. So if I had, for example, that's a great question. If I had this, if I had 1/2 x minus 3 squared plus 2, that A is less than 1, right? And therefore, this graph shrinks vertically. Okay, now, if we did the same thing, but then stuck a negative in front of that 1/2, same equation with just that adjustment, the absolute value of A is still less than 1. So I want you to kind of keep them separate. I want you to think of a negative in front of A as a separate thing. This is telling me to reflect. Right? So then if I had, let's just try another one. What if I had this? Y equal to negative 3 times x minus 3 squared plus 2. Now, is that telling me that my graph is shrinking? Or is my graph growing vertically? That negative in front, so it's throwing you off, huh? All right.
I don't know what you mean by like absolute value.
You don't know what I mean by it? Or
Well, I
you?
mean, I know what you mean by it, but I don't know what it means.
Okay. So whatever that thing is in front of it, just imagine that thing having absolute bars in front of it, which means this absolute value of negative 3 is a 3. Graph stretches vertically. But that that negative then, again, it's just telling me I'm doing this. I'm reflecting the graph. So instead of opening up, it's going to open down. Remember that? So maybe you do this. You look for the negative first. After you've decided you got the negative, then you get that out of the picture, and now you go look for your A. Does that make more sense to do it that way? Good deal. So there it is. If an A is negative, then we do a reflection vertically, which means, and we talk about movements here in just a second, they switch my up and down. So when instead of moving up to the graph point, I'm going to move down. Or if I move down first, I move up. So that's all we're going to do with this thing. All right. Are we okay on that? Yes? Let's see. Let's see what happens. Let's try one. So, well, we're not quite ready to talk about an example. Let's do this first. These are the parts. Hello. These are the parts that we will be looking for all of our parabolas or all of our quadratics. We're looking for axis symmetry. Once I know that, I can help me find my vertex. I'm going to look for whether the graph has X-intercepts, because sometimes parabolas don't. They'll always have a Y-intercept, but they won't always have X-intercepts. And then, depending on how the graph opens, I can determine whether it's a maximum or a minimum. So, let's see. How many of you guys had Algebra 2 with Lockray? Anyone have Stedman? Stedman, talk about critical movements. Okay. Is there anyone who is not familiar with that? Oh, all right. A few of you aren't. All right. So let's talk about this idea of a critical movement. To graph a quadratic, I can use this to graph anything that's a parent function. So what is a parent function, first of all? So we have 9 parent functions that we have looked at. Maybe not 9 for you guys, but we've had, well, there are up to 9 that we have looked at in the past that we call the parent functions, because we haven't tweaked them at all. We didn't add anything to them. We didn't multiply them by anything. They're just raw, pure raw form, no coefficients or constants. Like here, y equals x squared. That's a parent function. There's no number multiplying. There's no adding. Nothing going on with this. Just y equals x squared. So if we can understand what's going on with the parent functions in terms of how you move from a start point to create the graph, then you could use those movements. And once you start to translate a graph and stretch a graph, you can apply those movements to that graph. Hello, sir. But let me tell you first of all, before we get going too hot and heavy on this, is that just parent functions are really derived from coordinates. That's where we get them from. How do we determine that the parent function movements of a parabola are these? -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. Well, if I plug a -2 in for x and I square it, I get a +4. If I take a -1 and I square it, I get a 1, and so on and so on. So that's all that these have done. These critical movements are the result of me plugging x into that equation and finding y. So that's it. Now, what about them? In the x world, a positive x means to go right, and a negative x means to go left, just like a number line. And in the y world, positive means to go up, and negative means to go down. So then when you see these coordinates that have now been referred to as critical movements, you think of them as right, left, and up and down. Don't think of them as x's and y's per se. Think of them as right, and left, and up and down. So if we graph a parent function, first of all, the parabola has a unique starting point at the origin. Plug a 0 in for x, you get a 0 for a y. So it has that starting point of 0, 0. And from that starting point, I would go left 2 up 4, and left 1 up 1, and right 1 up 1, and right 2 up 4. And those your parabola. Going through those points. All right. Say that again.
Would you have given us those points?
No, you're going to need to know them. But here's the deal. We won't leave you in a lurch. Because if I didn't give you any information about critical movements, if you've never heard of them before, and I saw an equation y equals x squared, what would you intuitively do? You'd just start plugging numbers in, wouldn't you? Right? Some of you may cry. But most of us would probably know what to do. We'd say, oh, I don't know what this graph looks like, so I'm going to create a table. And I'm going to plug some x's in, and I'm going to find some y's, right? So that's always your default mode. If you need to be rebooted, come in and get some help. But that's always a default. I can just plug some x's, find some y's. Yep. All right. Good question. So there was our graph, right? That's what it looked like. What about these parts? Because we need to identify all of these parts, right? A vertex and a line of symmetry. You know, probably, they're all stuck together right now. Line of symmetry I would want to find first, because I can't find the vertex unless I have a line of symmetry. Unless you are in vertex form. Then you can find the vertex first. All right, so going back to our graph, maybe I should have disconnected it here. There it is. Looking at that thing, vertex. We haven't really formally talked about what the vertex is, but what would you guys, because you already know about this stuff, how would you describe a vertex of a parabola? Well, in your own words, what would you say to somebody who hadn't seen it before and you're describing this? You know, there's this cool thing called a parabola. Yeah? Well, see, your mouth's full right now, so you... What would you do? In your own words, people, come on.
Describing
Yeah, how do you describe a vertex to somebody?
vertex?
Yeah.
Like
A starting point, a coordinate.
they can't go
Oh, go ahead.
the most release.
Huh?
The most release.
Okay, yeah, that's a good way of thinking about it. It's the biggest value of y or the smallest value of y, right? So Bobby said it's the top point or the lowest point. Yeah. It's going to be either the highest point of a parabola or it's going to be the lowest point of a parabola. That's how you would describe a vertex. So in this case, our vertex is the lowest point because our graph is opening up. Why is it opening up? Why? Because A was positive, so it opened up, and every time a graph opens up, you have a minimum vertex. So minimum just means I'm at the lowest point. So there you go. That would be our. So that little dude was our vertex. There we go. All right, we know based on this graph that this vertex hanging out at 0, 0. Not all vertex will be at 0, 0. Because sometimes they're going to move around. Now, line of symmetries, this is a good deal. If you know what a line of symmetry is, you'll know that that is always this. Whatever your x part of your vertex is. Whatever the x part of your vertex is will always be your line of symmetry. All right? X equals 0 is my line of symmetry. That's that magic line that cuts my graph in half. It's this symmetrical piece. All right, X-Intercepts, this one only has 1. It's the same thing as the vertex. But that's not always the case. And also, unique here, the y-intercept is the same thing. So we got a vertex, a y-intercept, and x-intercept all being the same thing. That will only happen with a parent function that has been stretched but not moved. And then now, because this graph opens up, we know we have a minimum value at the vertex. That's what that means. What's going on? Is the vertex the biggest point, like you guys are saying, the highest point or the lowest point? This one is the minimum, is the smallest. So there's our review of parent functions, and then now we're going to start to manipulate things. transformations. Transformation. So here we are, first one. We're transforming our normal parent function. What looked like before a y equal x squared has now been altered. It's been altered in two different ways. It's got this plus 2 that's stuck with the x. Notice it's on the inside of the parentheses. That's important. Things that are stuck with the x on the inside of the parentheses of a function are talking about horizontal translation. Translation is the same fancy word for a movement. Translation, left, right. So anything with the x is a movement, right or left. And then the constant that's out there is a movement up or down. That also is a translation. So in this case, first of all, what form are we in? We're in vertex form, which is nice. Because when we are in vertex form, I can automatically find very quickly actually two things. What are the two things I can find quickly with vertex?
Origin.
Vertex and minus symmetry. All right. So my vertex, remember, is the HK from my vertex form. So maybe you get in the habit of writing this down. The more you write it, the easier it's going to be to memorize it. So you look at that, and you go over here, and you compare with the equation that we've been given, and you identify which parts are H and which parts are K. What's my H look like? A 2? Or a negative 2? Yeah, that's the question. What is it? 2 or negative? Notice in the equation it goes x minus h, and this is x plus 2. So opposite. It's always opposite. So my h is a negative 2. My k, if it's with the x minus something squared, it's on that side of the equal sign, it's not with the y. Your k is what you see is what you get. Meaning, if it says negative 3, that's what it is. So there we are. Negative 2, negative 3. So we're going to come over here, we're going to graph it. Negative 2, negative 3. That's the vertex of my graph. Now, from there, we know that my graph has to do one of two things. It either has to open up from that point or it has to go down. All right. Good. Now, because we know the vertex, what's the line of symmetry? Oh, very good. I'm pleased that you said x equal, because that's what a line of symmetry is. It isn't a negative 2. It is a line. And a line is defined by an equation. And this is a vertical line, and so therefore it's defined by the equation x equal negative 2. So if I ask you for a line of symmetry, do not just give me the number. Line of symmetry is a line. It must have an equation. Are we clear? Wonderful. All right. Open up or down? What's it doing, folks? Who said that? How do you know it's opening up? Because what's positive? No, hang on. Whoa, whoa, hang on. Be careful now. Parabolas don't have constant slopes. It's not a line. Right. The A, very good. The A is positive. How do we know there's an A? I don't see anything hanging out right there. It's a 1. Yeah. It's a 1. So if it's a positive 1, that means it opens up. And if it opens up, that means my graph has a minimum value. Because it opens up. A is equal 1. What in the world is that? 1. That means it opens up. That means it has a minimum. All right, so we know my graph's going to open up. Okay, these next two now. So now we got some stuff we got to do here. We got a little work ahead of us. X-intercepts. How are we going to find them? Plug what in?
Numbers.
Okay. What do you mean X values? Give me a little more. A little more to go off of just X values. So. Very good. You guys are kind of on the right path, both of you. You've seen it, nailed it. If I want to find X x-intercepts, I make y equal 0. Now look what happens when you do that to an equation that's in parabolic or vertex form. If I make y equal 0, I get this is equal to x plus 2 squared minus 3. So how would I solve that? Yeah, use your mouse now.
You can isolate the.
Isolate.
So
That's a great word.
So add 3 to the.
Okay, add 3, so I get a 3 is equal to an x plus a 2 squared.
Then square root.
Then I square root both sides, and we're going to have to go down here because I didn't have enough room. And we're going to get that plus or minus the square root of 3 is equal to x plus 2. And then I go x equal to negative 2 plus or minus the square root of 3. There they are. There are your two x-intercepts. One of them is negative 2 minus root 3, and the other one is negative 2 plus root 3. Now, you're going to probably convert those to decimals because it's easier to graph them. Negative 2 minus root 3. Root 3 is like 1.7. Is that what it is? So if somebody get on the calculator and tell us what negative 2 minus square root of 3 is, then do the same thing for negative 2 plus square root of 3. Anyone? Anyone? Numbers? Numbers? Mr. Locke.
For the plus,
Yeah.
it is negative 0.267.
Negative 0.268. All right. And then how about for this guy?
That one is 3.732.
Negative 3.732. All right. Now we're just graphing these, so we don't need to take it out to the thousandths place. But negative 3.7 and positive or negative roughly negative 0.3. So negative 3.7 looks about right there. Negative 0.3 looks to be about right there. Those are my x-intercepts. Those x-intercepts are equal to those two things. Okay. Great, great. Y-intercept. How do we find the y-intercept? We make x equal 0. See how easy this is? Really? I mean, come on. Challenge me. All right, so we get y is equal to 0 plus 2 squared minus 3 because we're going to make y's, or x is equal to 0. And then that becomes, what does that become? 1, because 0 plus 2 is 2, 2 squared is 4, and 4 minus 3 is equal to 1. And so my y-intercept is equal to 1. There we go. Y-intercept is equal to 1. Now, what can I do on the other side? You have a mirror image, symmetry. Can I put another point on the other side that's the same distance away? Yeah. So I have, remember, you have this vertical line here, which is your axis of symmetry, which means you can mirror image any point on the right to the left or left to the right. So if I have this point that's 2 to the left, I'm going to go, or 2 to the right, I'm going to go 2 to the other side. And now those 2 points are mirror images of each other. And that's just, I could do that to help me graph the graph. I don't have to. I have enough. I have enough to be able to draw this beautiful shape. Nice parabola. Okay, and it opens up, and there it is. I think we've answered all of our parts, haven't we? Answered all of our questions. All right, so here's your chance. Speak up, because you're going to get time to do one on your own. Any questions on the graphic component or the part component, how we're finding the pieces? No? Well, you guys, you're either lying to me or you just know you're wrong. All right, let's try it then. Let's try these two. I know you can partner up with somebody if you want. All right. A parent function. That's a great question. Why didn't we just graph a parent function from this thing? We could have. Watch what happens. Watch the magic of the dot. First of all, is our function here being stretched or shrunk vertically at all? No. So that means we can use our parent function movement. So watch this. It's amazing. If I go from the start point, now all your movements have to come from your vertex. That's why you have to find it first. So if I go from my vertex and I go left 2 and up 4, that puts me, oh man, get out of here. Go left 2 and up 4, that puts, oh, get out of here. Left 2. Here. I go left 2 and up 4, look at that. And then I go left 1 and up 1. And I go right 1 and up 1. And I go right 2 and up 4. It was the same graph we just generated, right? It is amazing. Math is a 4-letter word for amazing. So there it is. It's the same graph. So can you always use parent function movements if you know where the vertex is? The answer is yes. Every time. That's the beauty of it. Every time. So now we go and we take a look at these. And you guys had a vertex of 4, 1. So we go right 4, up 1. There's my start point. We looked at my A, and the A is equal to 1, which means the graph opens up, which means it has a minimum. And if the graph opens up from a point above the x-axis, you'll never hit the x-axis. So we can go do our movements now. Left 2, up 4. Left 1, up 1. Right 1, up 1. Right 2, up 4. There's my graph. Doesn't hit the x-axis. All right, so we're going to see why. We're going to let the math prove it to you that there are no x-intercepts here in just a second. So we go down here. We've already found our vertex, 4, 1. Because we know our vertex, we know our line of symmetry is x equal 4. Now, conceptually, we see that there are no x-intercepts. But why, mathematically, are there no x-intercepts? Well, what we usually do is we set y equal to 0. And then we say x minus 4 squared plus 1. Well, if I took this thing and I tried to solve it for x's, watch what happens. I get negative 1 equals x minus 4 squared. And then I take a square root. And there is the problem. If I take the square root of a negative value, you automatically have no x-intercepts. Because you're getting an imaginary value here. No reals. So there are no x-intercepts. None. And then what about y-intercept? Well, we could keep going, right? We can't see it on our graph. But I could keep going graphically, but why not just solve it? And how you solve it for a y-intercept is you set x equal to 0. So now you have 0 minus 4 squared plus 1. And that's equal to 16 plus 1, which is equal to 17. So I know that my graph has a vertical intercept way up there outside of my little chart that I've got going on here. It's going to hit at 17. And then we've already answered this one. It's already a minimum because my graph is opening up. All right. What's this one doing? Let's just talk through this one together, shall we? Where am I starting? Where's my vertex on that second graph?
2, 4, 4.
2, 4. So I have a 2, 4 HK. Okay, why all of a sudden is the board orient? What's going on? Okay, so 2, 4. That's not 2, 4. That's not 2, 4. That's not 2, 4. That's not 2, 4. That's 2, 4. Okay, so there's my graph. I have 2, 4. Is the graph opening up or down? There's that negative, right? There it is, camping out in front of my parenthesis. So this negative right there, that tells me that I have a maximum vertex value, which means my graph is opening down. Do I have any stretching or shrinking going on vertically? This graph? No. So let's talk real quick about how do the critical movements work now that I've got this negative down front. All this does is it takes my critical movements. Left 2, left 1, right 2. And it makes my y's become the opposite of what they are. That's all that it does. So instead of being an up 4, I am now a down 4. And now I'm a down 1 and a down 1 and a down 4. That's all that it does. So we graph those movements. So from our point here, we go left 2, down 4. Then we go left 1, down 1. And right 1, down 1. And right 2, down 4. There's my graph. There. Isn't that cool? It is so cool. X-intercepts, we can physically see them. 0 and 4. Y-intercept is 0. So we're able to answer the question for us. So that's all you're going to do. That's why critical movements are so beautiful. They're beautiful. Because all you do is I tweak these values. If I have a stretch factor, guess what I do? I multiply y by whatever that stretch factor is. So if there's a 4 hanging out in front of that, this becomes 16, 4, 4, and 16. So now instead of going left 2 up 16, left 2 up 4, I can go left 2 up 16. And I'd still be able to draw my graph. And butter, like butter. All right, now those were done with the vertex form. How do we do it when we're not in the vertex form? Well, people, I'll show you how. I'm going to show you a couple ways you can do this because, you know, I got the tools to do that. We're going to do method number 1, which is finding my axis of symmetry. You guys need a break? Need a break? All right, let's take a break. Take a break. So now we're in standard form. Remember, standard form is ax squared bx and c. So look at my graph. Is it opening up or down? Notice that the a in the standard form is the same a in vertex form. Maybe. So if my a is a 2, am I opening up or down? Okay, now what is the 2 doing to my critical movements? Vertically stretching them. So now all of my movements, which are normally left 2 up 4, now becomes a left 2 up 8. And a left 1 up 1 becomes a left 1 up 2. All right, so that's all that's different. Now we find our vertex differently too, because I don't have it kind of screaming at me. So what we do to find our vertex is we use our negative b over 2a line of symmetry equation. So we find a, we find b, we plug them in. So negative 4 over 2 times 2. That gives me a negative 4 over 4, which is a negative 1. Now that's not the vertex. That's the x part of the vertex. So remember that. A vertex is a coordinate. And we've only found one of those parts of the coordinates. So far, I've got this vertical line at x equals negative 1. Somewhere on that line is the vertex camping out. Okay, how do I find the other part then? I plug it back in. Exactly. I plug negative 1 back into my equation. So I take this value, and wherever there's an x in my standard form, I'm going to replace it now with a negative 1. And I'm going to be careful when I do this. For example, let's do it over here. So I get a 2 times a negative 1 squared plus 4 times a negative 1 minus 6. Negative 1 squared is 1, and 1 times 2 is 2. And minus 4, and minus 6 gives me negative 2 minus 6, or negative 8. That is the other part of my vertex. Negative 1, negative 8. And then from there, everything else is going to be the same. Finding these parts. We already found the line of symmetry, right? There it is right there. So x equal negative 1 would be my line of symmetry. All right, how do we go about finding the x-intercepts now? Yes. It's what's supposed to be. Negative 1 squared is 1. And 1 times 2 is 2. Okay. Yeah, always got to check. Keep me honest. So how do I find the x-intercepts? Don't think the rules change. How did we do it last time? We set y equals 0. Still the same thing. We still set y equal to 0, but now you're doing it, and we're going to have a quadratic. So I'm going to have 0 is equal to 2x squared plus 4x minus 6. Now I could factor a 2 out here, or divide everything by a 2. You get x squared plus 2x minus 3. And then I factor this, and I get an x plus 3 and an x minus a 1. And this equals 0, which means that my zero product property would tell me that one of my zeros is x equal negative 3, and the other 0, or x-intercept, is x equal 1. So we come over here, negative 3, put a dot. At 1, put a dot. At negative 1, negative 8, put a dot. Oh. Can we see the shape of our graph? Can we get an idea of what it's doing? Yep, we can. Now remember how we talked about a little while ago, our stretch factor? From our vertex, we would have normally gone left 2, up 4. Now look what happens. We go left 2, up 8. And that puts us right at that x-intercept. And right 2, up 4 is now a right 2, up 8. And that puts us at the other x-intercept. So the only other point we're missing, if we want to use them, is a left 2, up 2. And a right, I'm sorry, left 1, up 2. And a right 1, up 2. Now, I'm able to draw my graph. Yes, Simon?
How did you get the 1, 0, the right?
How to get the 1, 0. All right, so we're taking 2x squared plus 4x minus 6 for factoring.
Yeah, it was negative 3, 1.
Correct.
Isn't that 1 point, or is that 2?
No. Those are two different x values. X equal negative 3, x equal 1.
Okay.
Yes?
And then the y-intercept is just negative 6.
Exactly. So, yeah, the nice thing about the standard form is that the y-intercept is always your c value. So if we write it as a coordinate, it would be 0, negative 6. And look, that's where it is. 0, negative 6. So I have everything I need to draw my graph. There's my parabola with the vertex hanging out on this line. X equal negative 1. So not a whole lot different other than negative b over 2a. And that's really the only thing that's different. Okay, now here's where it gets fun. This is where it gets exciting. Method 2. This is the second way that I can. Some of you would prefer to work in vertex form. It's easy to see the vertex, easy to see the line of symmetry. Ooh, that was a scary face. You're right.
Yeah.
Okay. All right, so we already know from the last problem we did, look at it, it's the same thing, right? Same problem as we just finished. We already know that this vertex happens at negative 1, negative 8. So let's show how we can complete the square and figure out that I'm going to get the same thing here. All right. Now, before we do that, here's what I'd like you guys to try and do. I would like for you to try and take those coordinates of negative 1, negative 8, which are your h and k, and write the standard or the vertex form of this equation just from that information. Are you able to do that? Are you able to take that and put it into this form? Yes or no? If you think you are, go ahead and try and write the vertex form of that equation. Now that we know h and k. it appear that we're missing?
The A.
Very good. But are we?
Choose the A.
Yeah. The A is already the thing that's hanging out in front of the x squared anyway. So we know what the A is. We know the A is equal to a 2. So we actually knew all of the parts that we need to be able to write this equation. So when we're done with this thing, it better look like this. We hope it looks like that when we're done. So let's see how does this work. We're going to complete the square on this. We've just been completing the square chapter ago, so it should be fairly fresh in the brain. The only thing that's a little different about it is instead of there being a 0 on one side, I've got this f of x. So I'm going to show you completing the square two different ways. I'm going to show you your way that you're familiar with, and that's if we move the constant to the other side. And I'll show you a way you can do it also where you don't have to move the constant. So we would look at this and I'd say, hey, I've got this 6, and that 6 is a constant. We're going to bump it to the other side. So this negative 6 is going to come over here and become a positive 6. So now I got f of x plus 6 equal to 2x squared plus 4x. That's what we would normally have done. Now this second step has a slight adjustment. What would we normally do in completing the square right now for this problem? Not B, not yet. We get rid of the 2. We get rid of all of the A's, right? We got rid of all the A's. We divided everything up by 2. However, we're not doing that now because we wanted it. If I divide everything up by 2, I don't have any more A's. So what we're going to do is a little different. Is you're going to just take out of the 2x squared plus 4x, just this binomial here, I'm going to factor out a 2. So it's going to look like this. 2 times x squared plus 2x. Now notice I didn't do anything with the 6. That's okay. The 6 is its own thing. It's on the other side. So now, look. 2. Oh, that's exciting. But we have to take this x squared plus 2x thing and somehow make this a perfect square. So now we can go back to our thinking about completing the square. And what we did next is we took the b, and we took half of it and we squared it. And my b right now is this 2. Bless you. And if I took half of 2 and I squared it, I get 1 squared or 1. Now, another slight tweak. So here, why don't we, here are the places where there's going to be a slight difference between our completing the square normally. That's slightly different because we only factor out the 2. We don't get rid of the a. Basically just divide it out, or factor it out. This next step, nothing was abnormal there. This one that we're going to do now is going to be a little adjustment to what we would normally have done. Simon?
Can you use the whatever form you're more comfortable with, or do you have to use that one?
Well, here's the deal. I can give you either form, and I want you to be able to go back and forth. So you should be able to go back and forth with both.
On a test, would you put like solve by completing the square?
Yes, I would. Or I would say, yeah, I would. I would say that.
How many points would you give us if we solve the way we know?
I would believe. I'm a pretty extreme individual.
All right, let's report.
All right, here we go. So Simon, just learn it. Learn it. All right, so here's what's new, the next step. Can you tell me what we would have done right here? What would we normally have done now? We've done half of b, we squared it, we added it. What would we have? We would have put it on the other side, right? We should have put it on the other side, but here's the thing. It's not just a 1 that I'm putting on the other side, because this 2 is partnering up with that 1. So what am I actually putting on the other side? A 2. I'm putting a 2 over there. Because I've added 2 to this side of the equation. That means I got to add 2 to the other side of the equation. So what's it, again, being careful, this next step, we have 2 times x squared plus 2x plus 1, where we are taking this and that, and we're adding 2 to the other side. So that's another tweak. So now what does it look like? Well, now it looks like this. F of x plus 6 plus 2 is equal to 2 times x squared plus 2x plus 1. Simplify stuff. F of x plus 8 is equal to 2 times binomial squared x plus 1 squared. Move the 8 back over. F of x is equal to 2 times x plus 1 squared minus 8, and that is what we should end up with. So, a couple little adjustments to our completing the square method. The tricky one being, whatever a is out front, that a multiplies by whatever I have added to complete the square on that trinomial. Multiplies and moves to the other side. Now remember I said you can do it 2 ways. There's one way. One way you can do it also is to not move anything to the left-hand side. Keep the 6 over here. And it would look like this. Let's kind of go from here. It would look like this. F of x would equal 2x squared plus 4x. Leaving the 6 there, we would do the following. F of x equals 2 times x squared plus 2x minus 6. F of x equals 2 times x squared plus 2x plus 1 minus 6. But, man, there's that 2 again. Take the scale. I've put 2 on this side of the scale, and it's now down here. There's no other arm on the scale. How do I make the scale go back into balance? I have to take 2 away. If I put 2 on this side of the scale, I have to take 2 away to make it go back. So there's the 2 that I have to take away. I subtract. Then f of x, 2, x plus 1 squared, minus 8. There you go. So that's without moving to the other side. Work on the same side, except now instead of adding both sides, what I add on one side, I take away. So that's your completing the square. That's how we go from a standard form into a vertex form. Very quickly we can just, hey, there's my vertex. -1, -8, it's stretched by 2. We can go off of that. All right, you're going to try this. I think we have one more here. Yeah, we're going to do this one instead because it's the same thing. But I'd like you to take, let's do, which one of those should we do? Let's do this one. F of x equals 3x squared minus 24x